Hello everyone, thanks for joining this session. Today, Yuanjian and I will introduce the optimization we implemented for Spark SQL called adaptive execution. So, first I will discuss some common challenges we have been facing in using Spark SQL, especially when the data size increase and the cluster size increase. And next, I will introduce what is adaptive execution and how it works and how it can address all the challenges we have been facing. And finally, Yuanjian will introduce their experience of using Spark and adaptive execution. All right, let's get started. So the first challenges we have been facing is to tune the shuffle partition number. We know this is by default 200, and this is very important for the Spark SQL performance. If you set this too small, the task will have more data to process. And if the memory is not enough, the data will be spilled to the disk. And this is bad for the performance. And even worse, OOM can happen, and this will fail the task. So however, if you set this too large, then the tasks finish quickly. So this will actually cause additional scheduling overhead. And when the task shuffle reads the data, it also means more I/O requests. And also for the last stage, it means you will output a lot of small files. So even as an experienced Spark SQL user, you may try to tune the number based on the imported data size and your total cost. However, we know there are a lot of stages in the single query, but you can only configure one shuffle partition number. So the same shuffle partition number doesn't fit for all stages. So our idea is to determine the best shuffle partition number for each stage at runtime based on the data size. This is what adaptive execution will do for us. The second challenge we have been facing is about the execution plan. We know the plan that Spark SQL chooses is very important for the performance. And for join strategy, we know Spark SQL will determine the join strategy at the planning phase. However, at the planning phase, Spark SQL may not know the exact data size of the import table. So in this case, even though the size of the import table is small enough for broadcast, but Spark SQL may still choose a sort merge join. So our idea of adaptive execution is to detect this at runtime. And when we observe that there's a better execution plan available, we can switch to a better execution plan at runtime. The third challenge that we have been facing is about data skew. This is, we know it's very common in joining tables. So this means that a task has more data to process, and this will be the slowest task. And this is a common source of slowness for shuffle join. Nowadays, there's no good ways to solve this. You may try to increase the shuffle partition number or increase the broadcast join threshold, but this only works in very limited situations. And also, you can try to add a prefix to the skewed keys and handle that manually. Again, this involves many manual efforts. So in adaptive execution, our idea is to detect the skewed partition at runtime and then handle that automatically for you. All right, before we introduce adaptive execution, let's review how Spark SQL works. So we start with the SQL query or the data frame program. Then Spark SQL analyzes it and generates the logic plan, optimize it, and finally generates the physical execution plan. So once the execution plan is generated, we know each node is the definition of the RDD transformation. So we can get the DAG of RDD based on this execution plan. Finally, the DAG is submitted to the scheduler, and the scheduler is able to divide this into a few stages at the shuffle boundary. So after that, the scheduler will submit the stages for execution. So the key here is that once the execution plan is determined, currently in this mode, there's no way to optimize the plan again at runtime. So in adaptive execution mode, our idea is to submit the stages one by one and collect the statics and try to optimize the plan in other stages. To accomplish this, we added a few more nodes in the execution plan we called query stage and query stage import. So in this case of joining two tables, this is a sort merge join. So we will actually insert 3 query stages for that. And when execution, we will start from the root query stage. So for the root query stage, it will find all its dependency. It has 2 child stages. So it will first execute these 2 child stages and submit them and collect their statics. So after that, we know the exact data size of the import. So now we have the chance to optimize the plan in this query stage. And also we can find the skewed partition and also determine the shuffle partition number. So now, next, let's take a look at all 3 main features in adaptive execution. So this actually, we know in the Spark upstream, this is also an adaptive execution feature, but our work is based on some work of that, but this is a new design and a new implementation. So currently, there are 3 main features in our implementation. The first one is to auto-set the shuffle partition number. We can enable this feature, and then we can also configure the behavior. So you can configure the target import size for a reduced task, and you can also configure the main shuffle partition number and the max shuffle partition number. So we will try to find the best shuffle partition number in this range. And here is an example. So suppose the target size that per reducer you set is 64 megabytes, and the shuffle partition number range is 1 to 5. So at the beginning, we will use 5, the max shuffle partition number, as the initial number. So in this shuffle raw RDD, there will be 5 partitions, and we collect the statics so we know the exact data size of that. At runtime, when we have all of this information, now we can check if we can use less reducers to process that. So in this case, we notice that partition 1, 2, 3 is small. So the total size of these 3 partitions is only 60 megabytes. So we can actually use 1 reducer to process these 3 partitions. So in adaptive execution mode, we can use 3 reducers for that. And if you set the min shuffle partition number to 4, then we will use 4 to make sure the minimum parallelism. The second feature is about optimize the join strategy at runtime. So in this case, the original plan is a sort merge join. But now, in adaptive execution mode, after we executing 2 child stages, we know the exact data size of the import table. So in this case, one table is 100 gigabytes, and another one is 5 megabytes. So we noticed that one table is small enough for broadcast. So in this case, we will optimize the plan to a broadcast hash join. And we will broadcast the small table. It needs, firstly, we need to collect the data to the driver and then broadcast that to all the nodes. After that, we will launch, for each map output, we will launch one reduce task to local read the whole map output and then join with the broadcast table. So after we change a sort mode join to a broadcast hash join, now there's no data will transferred from the network because we will let the reduce task local read the whole map output file. So this will greatly improve the performance. All right, the third feature in adaptive execution is to handle skewed join automatically. And this can be enabled separately. And there are also a few configurations to control the behavior. Currently, a partition is thought as a skewed partition if its data size or row count is n times larger than the median, and also larger than a predefined threshold. So suppose that partition 0 in table 1 is a skewed partition. And instead of using a single task to process the join of partition 0, we can use a few more tasks to do the join, and finally union the result. So in this case, each task will read a part of partition 0 in table 1, and then joining with the partition 0 in table 2. From the view of the execution plan, originally there's only one sort mode join. Now that join is still there, but it will only handle partition 1 to n. So it will not handle partition 0 now. And we add a few more joins to process partition 0 specifically. And after that, we use a union to union all the results. So in adaptive execution mode, because we submit the stages one by one, and we can optimize the plan in the later stage. So it's possible to update this plan like this. In this way, we can resolve the skewed join. So that's all for my introduction of all the features. And I know this is a short discussion, and if you have any questions to discuss, I will be at the Intel demo booth, so you can stop and we can discuss further. Next, let's welcome Yuanjian from Baidu to introduce their experience of using Spark and adaptive execution.
Okay, thanks for the detailed introduction of adaptive execution by Carson. Next, I will introduce some detailed user cases of adaptive execution usage in Baidu, and also some relative works about our team. Firstly, a simple introduction of myself. I'm Yuanjian Li, comes from Baidu Infrastructure Department and Distributed Computing team. Our team's responsibility is to support other business units like Search Service Group and the AI Lab of their requirements of Hadoop and Spark. And currently, I want, first of all, to describe some details about Spark in Baidu. This is old slides about Spark in Baidu, some metrics I shown the last year, also at Spark Summit. And in this year, we can see a rapidly increment both on the Spark cluster scale and also the daily job count. Currently, we hold about 9,500 totally cluster in 10 clusters in different Chinese places. And also, you can see the job count per day increment from 5,800 to currently the 18,000. With the rapidly development of user demands, the improvement of performance is very, very important, and maybe it is a killing feature of old Hadoop users transform and migrate their old Hadoop jobs to Spark cluster. So we dived deeply into adaptive execution with Intel guys, and we use all the features in our internal Spark version. Okay. During this half year's practice about adaptive execution, we mainly find these three scenarios which adaptive execution have very good effect. The firstly is some specific user scenes. This kind of things can hit the software join to broadcast join strategy. And the second is long-running applications or use Spark as a service. And the last is graph and machine learning applications. Next, I will give some detailed user cases and for these scenarios. Firstly, let's see the software join to broadcast join strategy. The common features in this scenario is small table in subqueries. Actually, because of the small table, the small is also a relevant concept here. Which is a small table? Should we identify and determine it? Actually, this, in some kinds of cases, it depends on the resource and also the user behavior. So it's a key point here. And if we hit this strategy, we can get the acceleration ratio from 50% to 200%. Here we show a detailed user case. The original user circle was on the right blue box, and it's logical, almost like the left. You can imagine that I currently has two big tables. They are base table 1 and base table 2 in the blue box. You can imagine that this two table has terabytes of data and maybe billions of rows. And also I currently has a target user list. The user list is special kind of table. Actually, this table is a set of user list. Mainly, this table has only one column and at most about thousands of rows. Actually, the user list generated from a website console, and our users click some button and get the user list from themselves logic. Currently, I want to get some generic aggregations result from both sides of the base table. So I write the circle here, and its logical is simple. I want to inner join with each big table and finally union them and get the aggregation finally results. So if I use original Spark version, you may find the physical plan like this. In the red circle, you may find that although the exchange, the base table is small enough, it's less about 10 megabytes. But the original Spark version still uses the sort merge join. After I opened adaptive execution here, you may find that here I use the broadcast join instead of the original sort merge join. This strategy can bring the circle from 20 minutes to the finally 7 minutes of almost the 200% improvement. Here, I just give a detailed user cases here, but in our practice during our usage, there is many of queries can hit this strategy. Okay. The second scenario is a long-running application. We divided this scenario into three. The first is long-running batch job. Generally, it's up to 1 hour. And the second is use Spark as a service. Like Livy, like Spatial, like Zeppelin, and also the Baidu Big SQL is our in-house Spark as a service based on Spark SQL, and also Spark streaming. The key point of this kind of scenario is we need adaptive parallelism adjust them. And here we didn't want to immutable parallelism number and within all the applications life cycle. So if we hit this strategy here, we can get the acceleration ratio from 50% to 100%. Here also a detailed user case here. We run this application in 100 instances, and each instance has 10 gigabytes executor memory and 4 executor cores. You can see the boosting stage was in red box. And after I open the adaptive execution, you may find that each stage has its own, the most suitable parallelism number. In this case, you can find that the number 13 and the number 7 stage has a boost improvement. This strategy can bring the duration from 52 minutes to 30 minutes, almost 100% of improvement ratio. And we also give 3 more configures here. They are the min and max number post-shuffle parallelism, partitions number, and also the target of post-shuffle input size. Okay, the last scenario, the graph frame and the machine learning lib. Here you may notice that I wrote the graph frame here, not graph X, because currently the adaptive execution based on the data frame and dataset API. So the old version of graph X and the ML applications based on RDD can't hit the adaptive execution. Actually, this kind of scenario has the same key point with the long-running applications. Both of them need the adaptively parallelism adjustment here. But we derived these 2 scenarios because almost the graph frame and ML lib applications has multi-stages of iterative computations here. So if we hit this strategy, we also have the acceleration ratio from 50% to 100%. Okay, with all above introduction of user cases, these 3 kind of scenarios, you may curious about how we found these detailed user cases and how we judge their acceleration ratio. Actually, it's impossible to do it by manual work based on the 18,000 jobs per day. Actually, we do this based on the metric system of in-house Baidu Spark cluster. And in these slides, you may find there is a module called rig agent, and it's responsible for aggregate and collect the metrics from all the, not only Spark, but also others distributed computing systems. Also, thanks for the features of Spark named metric sync. Here we have a customized metric sync, and we deploy it in our node manager and over all the hosts in our Spark OEM internal clusters. And during the application running, we collect the metrics through metric sync to the rig agent, and finally to a pub subsystem called Baidu Big Pub. You can also replace this use open source Kafka. And the prop application is one kind of special Spark streaming application running on our own clusters. It mainly collects the metrics from the Big Pipe and do some computing and puts the result to the Baidu Show X console. Based on this metric system in our internal Spark platform, actually we can get more useful information about the daily job count of the whole clusters, and also the daily job count divided into several clusters, and also the whole cluster's CPU usage. And our user can also use their application ID to search on the website and get their core application about my job. In this case, about the resource and also some CPU info, memory info, and also CPU usage and memory usage for this current job. At last, this is the result about the adaptive execution prop in our metric system. In this slide, you can see that we can get the clusters and the queue, the username, the application name, and also the most important is which strategy does this application could hit it. And we also send the emails and give some hints to the users and give some guidance for them to open the adaptive execution. So all of the work by Carson and me was now open sourced, and we also give some pull request to currently Spark master, and the Jira number is Spark 23128. If you're curious all about our features and want to try in your own environment, please check out. And also we do the work to commit the master, and the committers are now reviewing about the adaptive execution. That's all for our talks. Thanks all guys. Thank you.